Chapter 20. We're going to talk a little bit about your significance tests. We're going to look at the homework first, so let's look at that. You had 3 problems for homework. Hopefully you took some time this weekend to at least look over them. They were actually fairly short. I wanted to take a little bit of time just to kind of talk about the homework and how you approach that. Most of it was actually fairly easy, definitely short. So number 1 asks us to write the null and alternative hypotheses for each scenario. So if you have your book or if you have your homework, hopefully you have that out. If not, go ahead and be getting that out. If you didn't do the homework, absolutely you need to go look at the book. Well, this isn't really going to help you any because, well, you didn't take the time to think about it. So it's not really going to do you any justice by simply telling you what the answers are. The point was for you to think about it and come up with your own answers. Part A says this: a governor is concerned about his negatives. The percentage of the state residents who express disapproval of his job performance. His political committee pays for a series of TV ads, hoping that they can keep the negatives below 30%. They will use a follow-up polling to assess the ads' effectiveness. And so, obviously, if we assume that there is no such thing as a negative, or that his negatives are what they think it should be, right? They think that his negatives are increasing. So they're worried about his view being more negative than it currently is. So they think it's about 30%. So when we write our null hypothesis, we're going to assume the status quo. We're going to assume that what we're looking for is absent, right? It's no effect. So what we're thinking is it's not really going to be around. So our HO, obviously, is going to be the proportion is 0.3. The proportion of negatives is 0.3. The alternative here is that we're going to assume that the negatives, the ads, they think the ads will bring that proportion down. And so we want to check to see if that really worked. And so we're going to assume that nothing happens. If it really did bring his negatives down, then we're going to let the information or the data that we collect after that tell us that that's what really happened. In part B, let's see, it says, is a coin fair? And so this one, I think it would be very obvious. Fair would be giving you either side of the coin regardless of which one you chose. They're equally likely. And the point it says it's being fair, you could be unfair and either side of the coin could be more likely to show up. This is why we choose a not equal to alternative. It's not that it's more than 5, meaning that one side would have an advantage. Or it could be the other way around if you're looking to say the proportion of heads. That was what we were investigating. If we had a higher proportion for heads, then it would be unfair in the favor of heads. If it had a smaller percentage of heads, then it would still be unfair, except this time it would be in favor of tails. So it doesn't matter whether it's more or less than 0.5. It simply matters that it's not 0.5, because 0.5 means fair in terms of a coin. It's both equally likely to show up. All right, the next part would be part C. It says about 20% people who try to quit smoking succeed. Sellers of a motivational tape claim that listeners are listening to the recorded messages can help people quit. So here clearly we think that it's exactly what they claim it is, right? Nothing is special, still 20%. If this procedure, or if this tape, motivational tape, can do anything, then I want to let the data reveal that or convince me of that. And so we think that the proportion would increase because this tape is effective. And so that's why the alternative in this case would be that P is greater than 20%. Number 3, which was the next problem we had, was you had to read several statements about a p-value, and this is super important. Number 4, question number 4, which was not assigned, and I'm not even going to assign it tonight, but it's a really good question. You should definitely take time to look through things like this. Hint, hint, multiple choice questions. Good questions for tests. Just going to leave it right there. Number 3, it says a couple things, right? You got 4 choices, and it's talking about each time it says there's a % chance of something happening, of the ads working or the ads not working, or that their results were correct or not correct, and that is not what a p-value is. We'll talk a lot more about what a p-value is in chapter 21, but we'll just kind of I'll read the correct answer. There's a 22% chance that natural sampling variation could produce a poll result like this if there's really no change in public opinion. That kind of sounded really obvious that was the answer, because it was obviously the most technical answer. A p-value is a conditional statement. What we mean by that, we say we're going to assume that something is true. So if this happens, then this is likely or unlikely to occur, or this is the probability that this would occur, right? With a p-value, whenever you're defining a p, just like in the last chapter, we defined the ways to interpret the confidence level, the confidence interval. There were certain things that had to be said, and they had to be in the proper light. You had to talk about them in a certain way. The p-value is a conditional statement that talks about the null hypothesis. Then it says that if the p-value is a conditional statement, we assume the null is true. So if the null is true, then the p-value is the probability that your sample would result in the way it did. And that probably isn't clear to you, what I just said, but with a lot more practice, you will get it. And so I guess the easy way to look at number 3 was the fact that they talked about a probability, and the p-value is definitely a probability, but they never talked about if the null was true, or giving some indication. In this case, the null was that there's no change in public opinion. So if there's no change in public opinion, then this probability, it was 22% chance, we would be able to see a sample with a result like we have 22% of the time. Notice the probability is related to the probability for the sample occurring. Not that we got it right, not that we know what the true proportion really is. It's none of that. And so be very careful. If you haven't read that section on p-values or how they interpret the confidence or the significance test, take some time and go through that. And definitely try number 4. Let's go on to number 20. All right, so this is going to pop up. I don't know why it keeps doing that. It's really frustrating. Anyway, number 20, it says, this one it's a scratch and dent question about a manufacturer of washer and dryers in a warehouse, and they have to determine whether if the damage is major or minor, and if it's too major, they have to note it as damaged and something like that. Anyway, on a random inspection one day, 60 washers were inspected, and they found that 5 of them had scratch and dents. All right, is this strong evidence that the warehouse is failing to meet their indication or their damage quota? They can't have more than 2%. And so if you look at this question and you think about it, you actually do the test, you could be misled. Here is an example of why we have to do our assumptions and our conditions. And so if we look at the rest of this, here's what happens. First of all, your first clue that there's something that could potentially be bad is that the probability of success is very small. It's only 2%. Remember, one of our assumptions and conditions is that I have to have actually 10 successes and 10 failures in order for me to use the normal model to describe the probabilities. Right? And so if you check your successes and failures, successes is going to be the big problem because we have only 2% chance of finding a damaged machine, which would be our success. And we can see here 2% times 60 is just 1.2. Not enough successes. And so the reality is that because this particular condition is not met, it means that I can't use the normal model, which means I can't use my logic and that certain probabilities are supposed to occur at certain places, right? And so we can't say anything about probability. Our sample size isn't large enough yet. So anything we were to say, there's no foundation, there's no validity to what we think about. So check your assumptions and your conditions. Note why we check the success and failure. It's because we want to be able to use a normal distribution to talk about probability, because that's what most of our probabilities are going to be based on, at least for now. Okay, so that was your homework. If you have any questions or if you need to pause that, rewind that, watch certain parts of it again, feel free. I want to go into a little bit more of notes. So pause the video if you need to and get out your notebooks. Get out something to write with, write on. We're going to kind of go through. I'm going to do an example. I'm also going to post this document on Classroom if you need to download it. It'll also be on my website underneath the video as well. So if you're at that place, you can click on it there. You don't have to go back to Classroom to get it, but I'll put it in both places. I'm going to talk a little bit about null and alternative hypotheses, and we're going to go in and talk about p-values. So effectively, I'm going to really finish up the notes for chapter 20 today, and we'll start 21 a little bit later, maybe tomorrow, maybe the next day. But chapter 20 is all about significance tests, and I want to make sure that you know how to do these 4 things. Number 1, how to write your hypotheses. Number 2, how to find your test statistic, which is our z-score. How to find the p-value, and how to write a conclusion in context of your problem. That's the 4 big concepts that we want to really make sure that we can do before we move on to chapter 21. In 21, we'll focus a little bit more on the p-value and what it means. And we're going to introduce some ideas called errors, type 1 and type 2 errors. But more on that when we get to it. So the null hypothesis, let's go over what the null hypothesis actually means. The null hypothesis is the statement where we're going to say this effect, this thing we're investigating, is not happening. We're going to assume that the status quo remains as is, that there isn't anything going on, and whatever I thought was going on actually is going on. The alternative, on the other hand, is obviously we're looking for an effect to be present. And so that probability is going to be where the alternative hypothesis says, well, this is what I'm expecting to happen. It's either not what I think it is, or it's more or it's less than what is currently happening. And like we did in number 1, we showed a bunch of different things that could change the alternative based on the context. And so with that said, I want to go over, your book does a really good job of talking about courtroom and how the courtroom does a really interesting or relative way of talking about null and alternative hypothesis. In any courtroom in this country, if you walked in to the courtroom, if you are on trial, then you will be assumed innocent until proven guilty. That's our court system. Take a minute, and while I'm talking, I want you to write down the null and alternative, and you can write it in words, and it won't be numbers because this isn't a mathematical scenario, but write it down what the null and alternative would be for the courtroom. Remember, now write it down while I'm talking, but the null hypothesis is the fact that we are assuming something, right? We're assuming the absence of what has been considered. And so you have somebody who is considered to have committed some crime of some type or something of that nature, but we're going to assume that which we are trying to see is absent, meaning that the crime that they committed did not commit. They did not commit. And so we assume that they would be innocent. The alternative to that would be that the case can build enough evidence for me to say it is very unlikely to see all this evidence if this person really was innocent. They don't have to actually be proven guilty. You just have to prove them mostly guilty. Enough to say that if this really was what happened, then there's no way that person is innocent. And so we will just assume that they were guilty. Unless, then this bars the fact, if you have the smoking gun, whatever, that's obviously going to prove them beyond a shadow of a doubt. And so if we write that out, here's what it would be. The null hypothesis would be the null is the absence of the effect. So we would assume that he's innocent of any charges. So HO would be the defendant is innocent. Just in the opposite side of that, we assume that he is not innocent. Or you could write guilty, since they mean effectively the same thing, but in math we would write not equal to, and in the first part it would be equal. So that's kind of why I put in this, right here, it's not innocent. And so you have the null and alternative, and if you have a hard time thinking about this, I want you to really pay attention to this example and the next example I'm going to give you, because it will help you in the long run to try, when you have to write null and alternative hypotheses, this is going to make up a good foundation that you can always think back on and think, okay, what's the null, what's the alternative going to be? Let me go back to that courtroom example. All right, so we're going to continue on. I got here Phantom, your favorite, and what I want to discuss, let me just delete this thing. I want to remind you, parameter of interest, hypotheses, assumptions, and conditions, name of the test statistic, obtain your p-value, and make your conclusion in context. This is what we are really going to be focused on for the next few weeks. In fact, most of our next semester, the rest of the semester, is going to focus primarily on all that kind of stuff. And so I want to look at page 467. It's going to be the example. It's going to be the step-by-step example about the home field advantage. And so the question kind of runs through some of the background of the Major League Baseball season in 2007. There's 2,431 games, and 1,319 of the home games played were won, which means 54.26%. Okay, so that's important for our test a little bit later. So the question they're asking is this: could this deviation from 50% be explained from natural sampling variability, or is it evidence to suggest that there really is a home field advantage, at least in professional baseball? And so if there was no home field advantage, then you would expect teams, and this isn't specific to any one team, you would expect the teams, if you broke it up into home and away, in terms of wins and losses overall, you would expect if they're about the same, there's no advantage of one place or the other, then you would expect to win and lose about the same in both places, right? If you take your wins and losses, you take all the winnings and say, well, how many did I win away? How many did I win at home? You would assume that wouldn't make any difference. So we're going to do a significance test and run through this. So I'm going to take you through Phantom, And I want you to pay attention, because this is how I expect you to do the problem when you're working these at home for homework, or on a quiz or test or anything like that, even the AP exam. So I'm going to run through this just like I would expect you to go through. So part P, this would be my parameter of interest. Now remember, this is the part, if you do leave something off, that's the one thing you can leave off and not get points from taken off. So the question we're trying to answer is the home field advantage actually a measurable effect? Okay. Are the proportions of wins at home significantly greater for any team in Major League Baseball? All my data is from baseball, Major League Baseball, so I have to make sure it applies. My conclusion is going to be about that. So we could make this apply to football or something else. Testing hypothesis part 2 would be your alternative. It's H, so it's your hypotheses. Well, remember we said if they're equally likely to win at home or away, then we would assume that the proportion would be about 0.5, meaning there's no home field advantage. You're not going to win more at home, or you would be about the same. And here is something we have to write an alternative. We assume that it is an advantage, so that would mean that there's more than a 0.5% chance of winning the games at home. The question is 54.26% too big, right? So if we go through it like this, randomization. So this is we're done with our hypotheses. That was fairly quick. And I wrote out words here. I just simply wrote that for description. You don't have to write out the words unless you just need to write it out to make sure that you've got it in the right way. Usually words can make it sound better, or maybe it can explain it if you're kind of unsure about what to write. Okay, our assumptions. I'm going to go through all 4 assumptions. And so we have randomization. Remember, this is a randomized game. This is a question in all of Major League Baseball. Right? So our population is really every possible Major League Baseball game ever played. Is there an actual home field advantage? And so, is it random? Well, we only have data on one specific season in 2007. And we have every team in 2007, but only 2007. Is this representative? As far as we know, we're going to assume that this season would be representative of any season or of all Major League Baseball games played. So we're going to consider this a random sample. We have no reason to believe it's biased in any way. Independence. This one seems kind of obvious. We're going to assume that one game's outcome has essentially, there are details, but remember, we don't want to worry about the exception to that rule. But essentially, that one game's outcome doesn't have an effect on the outcome of another game. And so they would be independent of one another. All right, 10%. Here's where you kind of have to know a little bit about what is my population? What am I trying to make a conclusion about? So we needed to know that we're really investigating all of Major League Baseball, or all the games that have ever been played. And if there were 2,400 games, 2,431 games in just one season, right? We multiply that by 10, that's 24,310. We know that of all the seasons, if you were to combine all the games, you're going to get a lot more than just 24,000 games. So we know that we have less than 10% of the population. So 10% is also satisfied. And lastly, we have success and failures. And we can look at this. We can say the 2431 times 0.5. I didn't actually write it both because it would have been the same number, so it would have been kind of redundant. So we know that we have 1,215.5, and you can leave that as a decimal, which it doesn't matter because it's well over 10 for our successes and failures. So that means the sample is large enough for me to be able to say, to use the significance test and use a normal probability to find out all the numbers and probabilities that we're going to try to find. All right, next part would be name the test. This one's easy since we really have only learned one test. It's a one proportion z-test. The test statistic. Now I've included the probability for the z-score. I'm sorry, not for the z-score, but for the standard deviation. just because, well, I want to make sure you remember that. And so I'm going to type in, because I totally forgot to do that, the z-score for this problem. I believe it was 1 or 4.0, 4.2. So the test statistic is z equals 4.20. And immediately, if you remember what you know about z-scores, that z-score is very large. Any z-score over 3.5, you would consider really, 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 really big, or really, really small if it's on the negative side. So in this case, we have a standard deviation, which is here. That standard deviation is used in calculating calculating my z-score. Now, I didn't have to use this. If you've done that one proportion z-test in your calculator, you know that the calculator is going to give you this back in, and I'll show you the printout in a minute. But I just wanted to make sure that we remembered what the standard deviation formula would be for a problem like this. The next part, obtaining my p-value, and so I kind of wrote down all the results that you would get from a p-value like that. And so it's under stat tests, one prop z test. You have a null hypothesis. That's what that p sub 0 means the null. What's the proportion that you wrote down in the nulls, which we wrote down 0.5 because we assumed that they're equally likely. The number of successes, in this case we had 1,319 home games that were won, and out of a sample of 2431. The alternative proportion, which is the section you come to here, is we think that proportion should be more than simply 0.5 because it is an advantage. It should be greater than 0.5. Our results, obviously the z was equal to 4.2, and the p-value is, and we're just going to write it this way because it's less than 0.001. So it's less than 1 out of 1,000. So extremely small probability in this case. So a couple of things I want you to recognize when you see a p-value like that. Number one, your results are very rare. They're very unlikely to occur given the standard scenario. Here again, this is something that people get backwards, get turned around, and the conclusion that comes from this takes a bit of time to get used to. Otherwise, you're going to get it backwards. So here's the conclusion. Notice I said if the null was true. This is where we're going back to that conditional probability about the null. If the null was true, meaning there is no home field advantage, it doesn't exist, then an observed value, meaning getting 1,319 winning games at home, or any more than that, would occur less than 1 out of every 1,000 samples. All right, so if we were to go and choose another year, say maybe we tried in 1960, or maybe we tried 1995, or any other year in Major League Baseball, and we were to conduct this study again, we shouldn't see results like this one except 1 out of every 1,000 times we do this, which is really small, meaning something is very wrong with this picture. So something, and if you think about what did I assume to be true? Because you know what happens when you assume, not good things. And so if what I assume to be true, if that's really true, then I would see this only 1 out of every 1,000 samples. And I think I did a pretty good job creating the sample, doing the test, so I don't think there's anything wrong with my process. So there must be something wrong with my initial conditions, my original assumption. So with a p-value so small, we reject the null. I have strong evidence, and the strong evidence comes from the fact that this is really, really, really small, right? If you were to say I've got a little bit of evidence, then you're probably talking things like less than 10%. Strong evidence would happen, once it starts happening less than 1% of the time, you've got some pretty strong evidence there. So I have strong evidence that the true proportion is not 50%. Okay, and we can go on to say, because alternative was a greater than problem, we would say that there really does, our evidence does suggest that there is a real home field advantage, at least in Major League Baseball. Be careful to qualify that, because home field advantage is discussed in lots of, or is apparent in all kinds of sports. So we would say that there does seem to be a home field advantage for professional or for Major League Baseball. Now, this is the process that I expect you to go through, and this is the process that you need to know in order to do the significance test, and to do them well and to do them thoroughly. Homework tonight is going to be from this section. So I'm going to go in here, and it'll, of course, be on Classroom as well, so you might have already even seen it. So I'm going to go ahead and type that in. If there's time left in class, I want you to go ahead and begin working on this. You can work on this in groups. You can work on this by yourself if you want to. Very important that you take the time to do the problems that actually have significance tests, like full-on significance tests. Take that time. See if you can go through the process that we call Phantom, and see if you can do the whole process. I think 32 is a good one. Probably the last three, 21, 20, 21, 22. 32 definitely is. Take some time. And I know some of you are complaining because I haven't put the page number up. Just calm down. It's the same page it was last time. Starts on page 477. So there's your homework, and I want you to take a little bit of time, whether that be in class or that be at home, and to go through this. We will start 20 and 21 really just kind of blur together. And so I'm really going to kind of start changing and start bringing in elements from chapter 21. So if you haven't read chapter 21, you might want to go ahead and look through chapter 21. At least not tonight. I mean, I'm not going to give you a pop quiz on it tomorrow or anything like that, so don't freak out about getting a quiz. But make sure you definitely want to start having a good connection, a good feeling for chapter 20 and the procedures that we've talked about here. If you have any questions, email me. I'm on email, regardless of where I am. If you need to watch this video again, the link is going to be on Classroom. It'll be on our podcast page, so you'll have access to that anytime and as many times as you want to watch it and ask questions.